Ramil, you're muted. You're muted.
Yeah, sorry. Right, so yeah, 10 minutes, and then I'll give you a warning at 8 minutes, and just with a panelist message. And then we'll have 3 or 4 minutes for questions, and then we'll switch over. Right. Okay, great. So yeah, so first speaker for this next session of SAZERAC 3B is Anne Hutter, and she will tell us about Estrellas.
Thank you very much, and I appreciate very much the opportunity to be able to present here our new framework to simulate early galaxies in reionization. And so we have building up this new framework, and using this framework, I also want not only present this framework, but also address like some of the outstanding questions, which is basically whether the universe got reionized by the numerous faint or the few bright galaxies. And in particular, I wanted to discuss like 2 physical processes that might determine this. It's like one is the escape fraction of ionizing photons, and the other one is sort of radiative in combination with supernova feedback, which suppresses star formation in low mass galaxies. So we're going to look at sort of, if you want to say, like 2 limiting scenarios, one where radiative feedback is rather strong, and one where the escape fraction of ionizing photons is basically enhanced for low mass galaxies. All right, so what is Estrellas? So Estrellas is, as I call it, a self-consistent model of galaxy evolution and reionization. That means it self-consistently couples both of them. And the aim is to have a framework that is fast and flexible and can scan the parameter space, so we can test lots of different models. And so what does it consist of? So the core is basically a dark matter-only in-body simulation, a semi-analytic galaxy evolution model, and a semi-numerical reionization scheme. So from the dark matter-only in-body simulation, we are basically getting the merger trees from the galaxies and the density fields. So from the merger trees, we run a semi-analytic galaxy evolution model in it. So we obtain then, we can evolve sort of the stellar masses, the gas masses of galaxies. And we also can compute like how many ionizing photons these galaxies are emitting. And since we know then each galaxy how many ionizing photons it emits, this ionizing emissivity distribution from the galaxies, plus that we know the positions of the galaxies in the dark matter in-body simulations, and we have their density fields, we can feed that into my semi-numerical reionization scheme and compute like how do the ionized regions evolve over that time step. And once we have done that, we basically know for each galaxy when its environment was reionized, and we can estimate sort of the radiative feedback from reionization. Okay, so what are the physical processes that we include in Estrellas? So first of all, Estrellas includes sort of the basic process of gas accretion, mergers, star formation. Then we have supernova feedback, which in our model basically suppresses star formation in low mass galaxies, because the most massive stars explode as supernovae and eject a certain amount of gas. And then the stellar populations in the galaxy will produce ionizing photons. These ionizing photons will escape into the intergalactic medium. They will start ionize the intergalactic medium, and due to the photoionization, the region will be also photoheated. So what happens is then you have this heated IgM, and the galaxy that sits in this heated gas. You have an instant increase, basically, or nearly instant increase in the temperature, which causes the gas pressure to increase. And the gas density, where sort of the galaxy sits, or on scales of the galaxy, decreases on a dynamical time scale of the galaxy. So actually, once a galaxy basically, its surrounding becomes reionized, you can call it the Jeans mass maybe of galaxy formation, starts slowly increasing with time. And this will reduce then, so this Jeans mass of galaxy formation basically gives you an indication how much gas a galaxy can hold. So what will happen then if your galaxy cannot hold as much gas but has more gas, the gas will photoevaporate, and vice versa, it cannot accrete as much gas as it could when it was sitting in a neutral region. So we can also quantify this, what we call the characteristic mass for the radiative feedback, and that's basically shown in this plot here. And you see the characteristic mass, which basically gives you an indication above which halo mass a galaxy is affected by radiative feedback, or below which its amount of gas is sort of suppressed, and also its star formation. And the key thing you see, like if, for instance, here the green line, if a galaxy sits in a region that was reionized with redshift 14, this characteristic mass will slowly rise with time, and only like far later reach basically the Jeans mass, which you would expect at the virial density. So there are basically two key points to take away from here. First of all, radiative feedback is not instant. And secondly, it increases over time. So in Estrellas, we have basically different models implemented. One is like really this rising characteristic mass, and the other one where we assume that instantly when the environment of a galaxy gets reionized, it jumps to the Jeans mass and virial density. So now you can imagine if the gas content of a galaxy, also its star formation, will depend on when its environment was reionized. And this is basically what I'm showing here in this plot. What you see here is on the x-axis, so to say, the star formation history of a halo with a halo mass, given halo mass at redshift 5, and as a function of when the galaxy's environment got reionized. So the top panel is like if we apply no radiative feedback. The bottom panel is when we apply radiative feedback. So what we see immediately, if we look at these two rows, increasing in halo mass from left to right, that radiative feedback affects only the low mass halos during the epoch of reionization. And the second thing we notice is that while if there's no radiative feedback, the star formation histories are basically independent of like when a galaxy or the environment of a galaxy was reionized. It becomes suddenly dependent on like when the environment of a galaxy got reionized. So going further, you can imagine that because reionization is patchy, not everything will be reionized at the same redshift. So basically in our simulation or scenarios, reionization proceeds in an inside-out fashion. So overdense regions are ionized before underdense region, as you can see it also in this plot here. And we can also then try to quantify this by looking at the ionizing emissivity distribution of all galaxies at redshift 7 for the case of no radiative feedback and adding radiative feedback. And here again, we see very clearly it only affects the low mass halos, and it affects the low mass halos. It suppresses basically the star formation and the ionizing emissivity contribution from low mass halos in the overdense region, while those in the underdense region, which are reionized late, are not affected. So that's a part of the radiative feedback. So for these scenarios, we have assumed that the escape fraction is constant. And so the question is like, having this contribution, how does it change if the escape fraction basically changes? So a bunch of radiation hydrodynamic simulations have indicated or shown that the escape fraction depends very sensitively on supernova and radiative feedback, and effectively decreases on average with increasing halo mass. So what we have done, we have used, since we have access to all the galactic properties, we have scaled our escape fraction with the ejected gas fraction that ends up with the escape fraction also decreasing with halo mass. And as you can see, while before the main contributor to reionization were between in galaxies lying in 10 to the 9 to 10 to the 11 mass halos, it now shifts to halos around 10 to the 9. And we can also quantify this even more by looking at the cumulative contribution to the total ionizing emissivity. So the way to read this plot is like, for instance, at redshift 6, galaxies lying in halos with 10 to the 9 to 10 to the 10 mass halos contribute roughly 30%, or the majority of the ionizing photons. If we add a stronger radiative feedback, we can see hardly anything of these contributions or fractional contributions changes. However, if the escape fraction decreases halo mass, the contribution by the low mass halos is very much boosted. So concluding is basically like the impact of the ionizing escape fraction of galaxies driving reionization is stronger than the impact of radiative feedback. And that brings me to my conclusions. So I think the key thing to take away, so the Estrellas is now, it's publicly available, at least so far the first release. We are working on, we have now a working version which is basically robust against the mass and time resolution of the underlying merger trees, and have started including metals and dust, which I believe will also be soon be released. So stay tuned. Thank you.
All right. Thank you very much for that lovely talk, Anna. So we can put questions in the Slack. So remember to put it under the appropriate thread in session 3B.
So there's one question. Jiang Qin asked, out of curiosity, in a SAM, how to get an outside-in reionization? Also, how long does it take for one typical run?
Yeah, okay. Achieving outside-in reionization, I think it's theoretically possible, but will be slightly challenging. I think what you might need to do is like change or boost the description for the self-shielding of the self-shielded region within the ionized region. So we actually have a description of like computing the residual neutral hydrogen fraction within the ionized regions, and you could boost that via a clumping factor or local clumping factor, and I believe maybe in that way you might get something like this, but I'm not sure, I haven't tested this.
The second question, how long did it take for one typical run?
Well, that depends very much on the grid size. For 128 cubed and for our current simulation, which is 230 co-moving megaparsec, resolving 10 to the 8.2 to 10 to the 11, 12-ish solar mass halos, it takes 6 minutes on 64 processes. If you go up then in the grid size resolution to 512 cube, you will be in the range of 4 hours on 64 processes.
Next question, Daniel asked, do you assume a single value of the escape fraction in the galaxy, or in other words, the homogeneous galaxy?
Yes. Currently, we assume for one galaxy, like one escape fraction, yes. And it's also homogeneous, emission.
The next question from Luke, do you put a constraint on the escape fraction, or can it be anywhere between 0 and 1?
So the way we have constraint parameters is by various observations. So like the UV luminosity function, stellar mass function, star formation rate, density evolution, the optical depth, and the ionization history. So the escape fraction theoretically can be between 0 and 1, but is basically constrained by the reionization history that we need to reproduce the optical depth.
Do we have time for one more question? Or?
Yeah, it doesn't look like a question so much as a comment, but yeah.
Oh, sure. Tom said the escape fraction of a galaxy is likely strongly affected by the radiative feedback from its stars, but you mean something different with radiative feedback, which is a bit confusing.
I guess he refers to the radiative feedback within sort of the ISM or the molecular cloud, really ionizing there the neutral hydrogen and providing the pathways for the ionizing photon. Yeah, I was talking basically about like if you heat the IgM from reionization. Yeah.
Okay, great. Let's move on to the next talk. So Laura, could you share your screen?
Yeah, sure.
And yeah, next we'll have Laura Keating, and she'll tell us about proximity zones. Laura,
Great. Yeah. So I'm just going to tell you about some work that I've been doing recently, trying to model proximity zones at redshift 6 and what that kind of means for the growth of black holes. And so first of all, what is a proximity zone? So this is just an example of a quasar spectrum at redshift 6. And as has been shown many times, the Lyman alpha forest is very saturated at this redshift unexpectedly, or expectedly, but close to the emission of the redshift, emission redshift of the quasar, there's a lot of ionizing photons coming from the quasar itself. And this allows for a more highly ionized intergalactic medium in the vicinity of the quasar. And so you can actually get a transmitted Lyman alpha forest close to the emission redshift of the quasar. And this is called the near zone or proximity zone. And what's cool about these proximity zones is they're sensitive to how long the quasar has been shining for, especially if it's like in the early phase of this. And so this is a plot from a paper from Christina Eilers showing the evolution of the proximity zone size as a function of quasar lifetime. And in gray here are results from sightlines from cosmological simulations post-processed with a radiative transfer code to mimic ionization by the quasar. And what you see is for shorter lifetimes, less than 10 to the 5 years or so, you find that the proximity zone grows with as the quasar has been shining for longer. And then eventually you reach this equilibrium value, which is set by the ionizing background in the IgM, where you're not so sensitive to the quasar lifetime anymore. And you can take an observed proximity zone size, which is shown by the red dashed line here, and compare this with the results from your simulations. And you can get a constraint on how long that individual object has been shining for, which is pretty neat. And so how did the observations look? So Christina Eilers has really spearheaded this in the last couple of years, putting together a really nice sample of observed proximity zone sizes. And so this is how a sample from her 2017 paper looks, with proximity zone as a function of the quasar magnitude. And the colors of the points are just the redshift of the objects. And so I can plot this equilibrium proximity zone size that I mentioned before on top of this. And what you see is for most of the proximity zones, it seems like a pretty good description. Like there's a bit of scatter, but they all kind of sit around it. But there are some objects that are really far away from the equilibrium value. And in subsequent papers, Christina showed that this isn't an unusual occurrence. About 10% of quasars in this redshift range have these small proximity zone sizes. And since a small proximity zone means the quasar maybe hasn't been on for very long, this is maybe a population of kind of young quasars. And so this is exciting because maybe it can kind of give you some idea about how these black holes are growing already at redshift 6. So Christina also had a really nice paper out on the archive last week showing the quasar lifetime, different constraints on the quasar lifetime over a large redshift range using different methods. And the proximity zone constraints are all shown here in blue. And you can see that the quasar lifetime can be, 10 to the 7, 10 to the 6 years, all the way down to below 10 to the 3 years. And this is maybe challenging for trying to understand how to grow these black holes, because these are really rare objects, like 10 to the 9 solar masses already at redshift 6. So you're going to have been accreting for a long time to grow that black hole already. So how to reconcile this with this very short proximity zone size is kind of tough to understand. So the first thing, we decided we'd go and try and look into this a bit ourselves. And the first question we thought about was, a lot of this work has been done using simulations with a uniform UV background where the IgM is already ionized. But what if there's still a lot of neutral gas in the IgM at redshift 6? And this is some work that I've been involved in over the last couple of years, showing that you actually need a significantly neutral IgM still at redshift 6 in order to match constraints from the opacity of the Lyman alpha forest. And this is just an example from one of the radio transfer simulations we ran to show this. So this is just a light cone through the simulations. The x-axis here is redshift, and the colors of the image represent how neutral the gas is. So if it's blue, if it's ionized, it's red if it's neutral. And the red box here just kind of illustrates where the redshift range of these observed small proximity zones are. And so there's still a lot of neutral gas in this redshift range, but mainly hanging out in the voids. So we took sightlines through the simulation, and again, post-processing with a radiative transfer code to account for ionization by the quasar itself, to try and see, could we actually match these small proximity zones, The answer was no. So again, we have this plot of proximity zone size as a function of quasar magnitude. The blue band is kind of the median result we get at each magnitude bin, and the shaded regions are like our 1 and 2 sigma contours. And we totally miss these small proximity zones. So they are very hard to reproduce in cosmological simulations, which has already been shown by other groups, but I think crucially here, even in models where reionization ends late. So the next thing we thought was, well, when we ran these simulations, we just assumed that you had one source and it was always on for like 10 to the 6, 10 to the 7 years. But of course, that might not be the case. Things can turn on and off. And we're not the first people to have suggested this. Fred Davies had a really nice paper back in 2019 putting out this idea, but we decided to look into it a bit more. And so this is an example of how this looks. So the black dashed line here is for a source that's on all the time. And you can see the proximity zone grows initially and then kind of settles to one value. And in contrast, we have a source that turns on and off. That's the blue line. And you can see that in this case, when the source is on, the proximity zone is very close to the equilibrium value that is found by the constant model. But when the source turns off, all the gas close to the quasar recombines and the proximity zone becomes smaller. So you can get this evolution in the proximity zone size with the quasar luminosity. And by just playing around with some of the parameters in these toy models, like how long the quasar has been on for and what the duty cycle of these bursts are, you can come up with something that kind of doesn't look bad compared to the observations. So the black here is a histogram of the observed proximity zone sizes just in one magnitude bin. The orange is for this constant model and the blue is for a time varying model. And you can see that the mean of the two simulated models isn't so different. They kind of both peak at about 5 megaparsecs. But in the time varying model, you get this nice tail of proximity zones that go out to quite small sizes that look reasonable compared to the observations. But of course, things that just turn on and off completely also aren't very realistic. We can expect it to be more stochastic. So we've also been looking in cosmological zoom simulations that self-consistently grow 10 to the 9 solar mass black holes. And this is work led by Tiago Costa at MPA. And so this is just an example through the simulation. So you resolve things both on large and small scales. This inset shows the galaxy that hosts the black hole. And the high spatial resolution of these simulations means we can generate light curves at 10 to the 4 year time resolution. And so again, we can look at a movie of how this is. So now in the top panel, I show the magnitude of how this light curve is changing. And on the bottom panel, I show the response to this on the proximity zone size. So the magnitude can vary hugely over a very short time scale. And the proximity zone itself can also change by a few megaparsecs. And we find that kind of in this particular sightline kind of just oscillates between two kind of set points, depending on whether the magnitude is high or low. And so what does this mean compared to the observations? Well, if I go back to this plot of near zone size versus magnitude and compare it to the black, which is the observations, and again, this equilibrium value, if I take all the points from that movie I showed and just put them on this plot, I get the orange. That's just for one single sight line and its evolution. And you can see that the magnitude can change drastically from -24 up to above to -27. And also you can get proximity zones that are very far away from this equilibrium value. And so we can also add in some results from just a handful of other sightlines. So each of these colored points here are just a run of one individual sightline. But what's really cool is even just for a few sightlines, we can really start to fill out the space in proximity zone size and magnitude, finding lots of sightlines that are close to the equilibrium value, but also lots that are really far away. And we end up with this population of small proximity zones with these simulated light curves, which is cool. So we can compare these to a constant model at a fixed time. So taking now a larger number of sightlines and looking at them all at 10 megayears. And again, just restricting ourselves to a narrow magnitude range, the same as the observations. So again, this black histogram shows the observed proximity zone size distribution. And the orange is just a constant model shining constantly for 10 megayears compared to our blue sample, which are flickering on and off and doing their thing. And again, we find that the mean of these two distributions isn't so different. So we still find large proximity zone sizes as you'd need to. But also we still get these nice tail towards the small ones, which again would kind of reduce the tension between the simulations and the observations. I will say that we maybe don't get enough of these small near zones. It's been estimated that they need to be about 10% of the entire population, which I don't think we quite get right. But there's other things that we're still not accounting for. Like there might be, obscured growth might play more of a role. In that case, you could have a shorter kind of on time for the quasar. But I think even more interestingly, there's been a couple of cool papers out in the last couple of months showing the role of the mean free path. And this is a result from George Becker's recent paper showing that the mean free path at redshift 6 is quite small. And this dashed line here is the result from the simulations that I've been working with. So you can see that the mean free path in our simulations is too big compared to what's actually observed. And Christopher Kane had a nice paper and a nice talk yesterday showing that one way to reconcile this difference is to add in kind of a subgrid model for substructure in your simulations. And so that would also help us, I think, to try and maybe boost the fraction of small near zones that we get, as well as these variable light curves. And so I'll conclude here by saying that just because you have a model where reionization ends late, it doesn't mean that you automatically produce a population of small proximity zones. What's maybe more promising is to have these models that can vary with time, and a toy model can already get you a pretty reasonable agreement. But actually models with light curves from simulations that self-consistently grow these black holes can actually show a population of proximity zones that seem in reasonable agreement with the observations, except maybe not as many as observed. So yeah.
Well, thank you. That was really impressive work. So yeah, if we have any questions, we'll wait for a little bit to see if questions show up on the slide. In the meantime, I guess I can just ask about that one simulation that seemed to oscillate between those two values of the proximity zone. Is that understood? Is that something about the feature of in the code or parameters?
So basically, I think it comes down to what this definition of the proximity zone actually is. So you take the spectrum and you smooth it, and the first time the flux drops below 10%, you say, okay, that's where the edge of my proximity zone is. So in that particular sightline, we found that there was like an absorber that kind of recombined a bit faster. So that drags down the mean flux to that point once you fall below a certain threshold.
Oh,
so you kind of have this value close to the host galaxy, and then another one kind of set by the IGM.
All right, here's a question from Slack. Very nice talk from Yuxiang Chen. How do the models perform in predicting large proximity zones or longer lifetime that are needed to grow these high redshift large black holes?
Yeah, so I think we do find our models do also predict larger proximity zones. So you see the largest ones here are at 8 megaparsecs, and we also don't have trouble reproducing those. I think mainly because these tend to be close to this equilibrium value, which is something that's kind of successfully reproduced by the simulations generally.
But I guess in your histogram, it did seem like you were short at the large zone. Or...
Yeah, I mean, there's also not so many observations, like there's only in this particular bin. So, and I think some of these also have kind of larger error bars. So I think just kind of in a general way, I'm not as worried about the large ones as I would be about the small ones. I'll say that.
Fred Davies asked, how often do you get the binary distribution of sizes for individual sightlines?
Yeah, so I guess looking at this, if you look at this plot, you can kind of see it happening reasonably often. So like say for this brown or purple, you kind of do get these, this bimodality, but also kind of then within kind of a cloud, you also have evolution. So yeah, it's kind of messy, I would say.
And then here's a question you sort of answered a bit. Would you say that we're missing small near zone sizes above the equilibrium relation, or they're just too rare in a simulation to be expected to be observed in current samples? So
you're asking, is there like a population kind of higher that we just don't see?
I think he's asking whether they're missing the object above.
I think the fact that we don't see them either in the observations or the simulations, like you do see sometimes that you can end up in this space, but I think you tend to scatter the other direction more.
All right, final question. What sets the small value of the near zone as compared to the equilibrium value?
So I guess this is kind of related to Ramil's value, like some or question. when the magnitude of the quasar dips, the gas starts to recombine, and you end up with a lot more neutral gas close to the quasar. And so this can suppress your Lyman alpha forest there, and you end up with a smaller proximity zone. And this can either just be kind of more diffuse gas, or it can be related more to an absorber.
Great, thanks. Yeah, you can continue discussion on the Slack. Meanwhile, we should switch over to Will's talk. So here's Will Roper, and he will tell us about the flares simulation. Here you go.
Right, yeah. So, oh.
Yeah, can you, there we go.
Oh yeah, sorry. Hi, I'm Will Roper. I'm a second year PhD student at the University of Sussex. And yeah, I'm going to talk about the sizes of galaxies at high redshift and flares, which builds on the work of some of my collaborators shown here. Chris, who will be talking exactly after this talk, and Ashwin, who will be talking later. So I'm going to start by giving just a quick primer on flares. I will try to make this quick, as you will hear this 3 times today, but flares is a suite of 40 zoom simulations. They're these 30 megaparsec spheres you can see rotating here. They're simulated with full hydrodynamics using the Eagle model and are pulled from a 3.2 gigaparsec parent box and simulated down to a redshift of about 5. And what this approach allows us to do is cover a really large range of overdensities from the extremely overdense extreme regions, which we focus on in Flares 1, which are up in the top left of this little animation, right down to the really, really underdense regions, which are down the bottom right. So anyway, with that primer out of the way, on to sizes. So when we initially looked at the half mass radii at these high redshifts, we were somewhat surprised by what we saw. So what you find are these distinct populations. So firstly, there's this high mass ultra compact population, which will be the population I'm going to focus on in this talk. And then there's also this low mass diffuse population, which is a whole nother topic in itself that I'm going to skirt around in this talk, but more than happy to talk about on Slack or just in discussions. And then you also have this third unimportant population, which is, I leave it in at this point purely to highlight that you should never trust your halo finder 100%. These are spurious galaxies that have basically been torn out of a parent galaxy just because there was a density saddle point. And in all future plots, they're recombined into the galaxy they were orphaned from. And another just sort of point of worry when we first saw these. So this high mass population are all below the half mass radii are all below the softening scale of the simulation. So yeah, initially worrying when we first looked at it. And just to quickly say, so this is the half mass radii relation, but across a selection of snapshots we have. So this dual population sort of evolution starts at redshift 12, it then continues throughout the time of the simulation. So right down to our final snapshot, 4.77. So the question stands, is there an issue in the subgrid model at high redshift, or is this actually a reflection of reality? And the only way we can find that out is if we compare to observations. So to that end, we create synthetic observations using synthobs, which you heard a bit about on Monday from Madeline. This was written by Stephen Wilkins, one of my supervisors. We take a bunch of stellar properties, input them to synthobs. That gives us fluxes for those stellar particles. And then we propagate the luminosities or fluxes of these stellar particles along the line of sight using code written by Ashwin to get dust extincted fluxes or luminosities. We can then take those fluxes and smooth them over some kernel, be that Gaussian, cubic, or quartic, or quintic, to create images that represent the underlying stellar population that the stellar particle represents. So, and from these images, we can then measure half-light radii. So this is the size and luminosity relation at redshift 5, but for the intrinsic luminosity. And unsurprisingly, this just traces the underlying stellar distribution. So you again have this sort of two populations of one bright, high mass compact, and one diffuse, low mass and low brightness population. But things begin to get interesting when you actually include dust. So this plot is again the size luminosity relationship, but now we're focusing on the the high mass population. The black points are the intrinsic from the plot before, and then the colored points are the observations with the dust included. And what you see, this increase in size when you're taking dust into account. So that's beginning to look a bit more promising now. We're not looking at these really, really compact galaxies. They're starting to puff up a bit, but the question is why? Why is this happening? And you might be able to guess sort of just by looking at and knowing your physics that it's the concentration of dust. So these exceedingly compact cores are producing metals fairly rapidly and seeding the core with dust, which then extincts the flux, and you actually see the outer edges much brighter than the inner parts, leading to a much higher perceived size when you're looking at the attenuated fluxes. But that's promising, but not actually comparing to observations. So now we compare in this plot simply to a Kawamata paper from 2018, and we see plausible agreement. So at these redshifts, the observations are fairly sparse, but really, really encouragingly, when we saw this, there was a good agreement between the fits from Kawamata and our distribution from the high mass compact population. The sort of caveat to this is flares focuses on these really extreme regions, and hence you get this large scatter at high luminosities, which isn't necessarily present in the sample. But sort of the obligatory point here being that, as we've heard this week, Webb will give us a wealth of data and we'll be able to hopefully populate.
Sorry, can we hold on for a second?
Yep.
I'm not seeing the slide for some reason.
Ooh, really?
Oh,
I see it okay.
Okay.
Maybe it's just me.
Don't know, it might just be lag.
Yeah, I think the rest of us are okay.
Okay. Sorry, in the interest of time, I'm gonna continue.
Sorry.
Yeah, no. So yeah, essentially we have a plausible agreement with observations, and I'm looking forward to getting a wealth of data at these redshifts to actually sort of nail it down a bit better. But I've sort of promised that I'm going to talk about evolution in my abstract. So with the time I've got left, I'm going to just quickly say, on the left here is the flares plot that I showed before of the half mass radii, the stellar half mass radii, and then on the right, I continue to trace that down through the Eagle reference box down to low redshift, and you can see at around a redshift of 3, so this panel here, the compact population begins to increase in size. So how is that happening? Why is that happening? And there's a few pieces to that puzzle, or 2 main ingredients, in fact. And the first is extended gas distribution. So these are just plots of the stellar half mass radii versus the gas half mass radii. And you can see that almost all of these stellar distributions are associated to an extended gas distribution. And it's just not star forming. And if you actually take a look at the compact gas populations, you see that they're all satellites. So there could be some halo finder effects in there. It's hard to say without diving in. The other ingredient that goes into this is actually the subgrid model itself. So in the Eagle model, star formations and stellar feedback are governed by the gas density at the point of star formation and the metallicity. And if you look at the evolution of those through to low redshift from flares into the Eagle boxes, you find a decrease in the density of star formation and an increase in the metallicity. So as the metallicity increases, it becomes easier to form stars in lower density. So this begins to, combined with the extended gas distributions, you get this picture of really, really compact cores that are undergoing runaway star formation at high redshift, and then at some point later around redshift 3, the metals mix just enough into the surrounding gas to begin their own star formation, and you get this puff up of the size of these galaxies. so just quickly to summarize that, we've found in the Eagle model at high redshift, you get these intrinsically ultra compact galaxies beyond stellar masses of 10 to the 9. But then when you actually include the effects of dust, we get a good agreement with the observations. And then obligatory Webb point. And then I've presented this plausible evolution track where you have compact cores surrounded by non-star forming gas that turns on at later epochs. And just to say, I'm going to be hopefully putting multiple papers from this up on arXiv soon. They're just all still in the works. And finally, and I might eat into questions ever so slightly to do this, but the what's next is quite exciting. So flares 2. We're going to aim for at least 10 times more regions. So instead of 40, we're going to have 400. This will allow us to cover various environments a lot better. And we're also going to run with the Swift hydrodynamic code rather than Gadget and the Eagle XL subgrid model. But possibly the most exciting part of this, and also because it just leads to other science entirely, is that we're going to be pulling from a parent at least 8 times larger, but hopefully 16 times larger than Flares 1. So this is a 12.8 gigaparsec box at the same resolution as the original parent. And what's exciting about that is, to our knowledge, it's the first DMO that's going to cover the entire Hubble volume out to Redshift 5 at this resolution. So I'm really looking forward to sort of killing some supercomputers with that. And with that, I will finish. Thank you very much.
Fantastic. Okay. Yeah, impressive stuff. So, yeah, do we have questions?
So Tom is asking, it might be worth comparing the density at which the stars form in the compact galaxies to the density above which Eagle supernovae feedback is known to fail.
So that's yeah, I have actually done that. So this mass regime at which you see the compact cores begin, so 10 to the 9, you can actually move that if you increase the feedback fraction. So there is some direct tie there. It's the old overcooling problem, basically.
Okay. Daniel is saying, nice talk. Which process can create these compact cores with sizes below the softening scale of the simulation?
Sorry, just think through the question. So it's more that so the way these form is you get these high density points within the gas distributions, and then they basically saturate the probability to create a stellar particle, and then also saturate the feedback. So the amount of energy that is given into the surrounding gas is maximal, but it's just not enough to have any effect on the density in that region. Which then means that you just keep amalgamating mass in a high density point, and then making it easier to form stars by seeding that gas with metals and not being able to puff it out into and mix it into the surrounding material. I hope that answers the question somewhat. It's sort of it's all in the subgrid prescription what actually drives this. If I have another, just say on Slack, call me out and I will try and do a better job.
Yeah, I guess I can jump in if there's not a question. So I was just, I mean, it is sort of following up on Danielle's point that it does seem to be fairly sensitive to this particular prescription for star formation and the metallicity dependence of that. Have you compared that to things like, there are some simulations out there with full H2 and stuff, and see if the metallicity dependence and density dependence actually follows the trend that's being assumed in Eagle?
No, I haven't, but it would be very interesting to do. We sort of discussed sort of as a collaboration, we discussed modeling H2 and doing comparisons there. Just haven't got around to it yet. But Yeah, there's some interesting stuff going on with the subgrid prescriptions that I probably can't talk about for future stuff, which sort of does tie into this to a certain degree.
Excellent. All right. There are no more questions. Then let's move on to the next talk. Thanks again to Will. And we're moving on to Chris Lovell. And Chris will tell us about passive galaxies in the ER. So yeah, take it away.
Thanks, Ramil. And yeah, thanks to the SOC for having me on here. So I'm going to talk a bit more about flares again. So thanks to Will for giving a nice introduction to the project. I'm a postdoc at the University of Hertfordshire, working with Jim Geach. This is some work I've been doing since my PhD at Sussex with Peter and Stephen, as well as some of their students, Ashwin, Will, Dimitrios, and Yusi, and also thanks out to the wider EU collaboration as well. So I'm going to talk a bit about passive galaxies at high redshift. So we heard a little bit about this on Monday with reference to some of the JWST programs. But so far from HST kind of programs, there's been evidence for passive galaxies out to about redshifts of 5. So this has been seen in a number of different programs. These have been selected both through SED modeling and also through kind of color selection diagrams. And you kind of see this evolution in the number density increasing with decreasing redshift to the present day. Compared to models, so some of the kind of state-of-the-art hydrodynamic models, there are actually quite significant variation between some of the model predictions. So these galaxies actually represent a kind of unique laboratory for exploring differences in feedback prescriptions in some of these models. So one of the questions that kind of comes to me when I see this is when and where do these very first passive galaxies emerge? Is this at redshift 5, or do we see passive galaxies at even earlier epochs? And obviously that would be of interest for some of these web programs that are actually going to be able to go a lot deeper in current observations. And what drives passivity during this kind of epoch? What causes a galaxy at these very early times when there's kind of abundant cold gas available to become passive? So that's kind of the motivation for some of this work. So as Will's already explained, flares is a series of 40 zoom simulations using the Eagle codes. This is full hydrodynamics. Each one of these is kind of a sphere, radius 20 co-moving megaparsecs, all selected from this large 3.2 gigaparsec cubes that matter only box. And we select a range of overdensities. So we've got these very overdense kind of protocluster regions. So these typically will evolve into clusters in the present day. So they're very overdense even at high redshifts. And it's in these environments that we perhaps expect to see more massive galaxies and perhaps more passive galaxies as well. So in the fiducial kind of periodic Eagle volume, it's about 100 megaparsecs on the sides. It's actually about 10 to the 4 times smaller than our parent box. So this kind of limits the different environments that you can sample in there. So flares is kind of a unique approach for studying these very overdense environments. So some early results kind of put on the archive last year, but it's just been accepted early this year, looking at kind of typical distribution functions, so the galaxy stellar mass function and star forming sequence and the star formation rate distribution function. So we see pretty good agreement with observational constraints in all 3 of these. And the particular thing with flares, we're able to extend the galaxy stellar mass function up to much higher masses and also produce much larger numbers of these very massive galaxies. So for this project, we were interested in passive galaxies. There's a number of different ways to select these, as we saw in the observational approaches. So we kind of experimented with all 3. So there's the specific star formation rate, so just a fixed threshold. You can also calculate the star forming sequence and then some distance away from that, which is shown by the kind of blue lines on here. Both of these are quite sensitive to the aperture with which you measure the specific star formation rate in the simulation. So in the Merlin and Santini papers recently, they actually state that, yeah, this aperture is incredibly important. So if you include larger areas, you may include kind of residual star formation on the outskirts, which then pushes your galaxy above your passivity threshold. So they use a definition of 4 times the half mass radius within which they calculate the mass and SFR. So we use a similar definition here, but it's worth noting that some of these definitions are quite sensitive. And then we also looked at these kind of color selections as well. So these are obviously slightly inaccessible at redshifts greater than 5 at the moment, but using BPAS as an SPS model, so this is binary population synthesis, and then Ashwin's 2021 line of sight dust model as well. So he presented that in a paper recently. He's actually going to talk a bit later about some dust radiative transfer predictions for flares, but these predictions are just using this line of sight model. We can calculate color selections, and we found that basically none of them sit within your typical Muzzin 2013 UBJ selection criteria. So we've actually defined kind of new selection criteria for these galaxies. If you wanted to select passive galaxies at redshifts 5 or above, for example. So the rest of the talk, I'm going to kind of concentrate on the specific star formation rate, just because it's a little bit easier, but we'll present those results in future work. So this is kind of one of the main results here is the evolution in number densities of these passive galaxies. So this is similar to the plot I showed before, comparing the different models. So the observational constraints here are shown in gray. The Eagle predictions from the periodic volumes up to redshift 5, slightly up to redshift 6, are shown in red. And then the flares predictions, which go out to redshifts of 7 or 8, are shown in blue. So this kind of neatly kind of extends the predictions from the periodic volumes. You can see it kind of matches up remarkably well. So this is using the weighting scheme from each of our Zoom simulations. So we have to weight the contribution from each overdense region or underdense region. And this seems to work remarkably well to agree with the periodic sims. And as far as I'm aware, these are the first predictions for these kind of passive galaxy number densities at these very, very high redshifts, at least from high resolution hydro simulations. So using the SPS and dust modeling from Ashwin's work, we can predict surface densities of these things and make predictions for JWST. So on the left, basically predict the number of objects per square degree at different redshifts, and for different kind of stellar mass cuts as well. Able to extend it again into the redshift greater than 5 regime. I've just noticed about 2 minutes before this talk, the numbers on the y-axis for this plot on the right are wrong, but there's just a normalization error there. But these are essentially predictions for different F150W cuts from JWST and the kind of detectability of different passive galaxies. And these are for all galaxies above a mass of 10 to the 9 M solar. So we're working on predictions, kind of tailored predictions for some of the cycle 1 programs now. So looking at kind of the intrinsic properties of these passive galaxies, they tend to be kind of centrals. They kind of populate the main kind of plot here is the one in the middle at the top here, populate the kind of upper part of this black hole stellar mass relation. So their black hole mass at fixed stellar mass is high compared to the majority of the population. 50% of the stellar mass, we define that as the formation time. We find that most of these things form between redshift 6 to 8. So those passive galaxies found at redshift 5. So they've formed within the last few 100 mega years. But there are a number of galaxies with kind of similar mass black holes that are not quiescent. So they're not a complete sample of black holes. So what's actually causing the quenching? So we've done a little bit of digging into this. So each of these panels here shows an individual galaxy at redshift 5 that's passive. And the blue line essentially shows the star formation history for that galaxy. The green line shows the assembly of the black hole, so the mass assembly of that black hole. And then the orange bars here are essentially when that black hole is accreting. And so hopefully the clear thing from this should be that there's a strong correlation between the black hole assembly and the decrease in the star formation rate. So essentially, as soon as the black hole turns on in the simulation, star formation is pretty rapidly quenched. And there's a few galaxies, for example, there's one in the bottom left where it remains passive for a few hundred mega years after that kind of AGN quenching event. So the AGN kicks in at around redshift 8 to 7, and despite little further growth in the AGN, it's actually efficiently stopped star formation in that galaxy for a reasonably long time afterwards. So this is kind of a first step with this. We're using Mega, which is a kind of tree-based or graph-based, structure finder that Will's developed to look at the kind of merger history of these objects and see whether the rapid assembly of the black hole is correlated with any merger activity. But as a kind of first test, we ran one of our regions with the AGN kind of turned off, and the kind of clear point with this on the left is that you don't see any passive galaxies in that kind of no AGN run. So it's clearly AGN that are causing passivity in these very high redshift galaxies. And you might note that some of these galaxies are actually quite relatively low mass for that to be the case, but we noted in the first paper that the kind of characteristic mass at which the AGN turns on is actually a lot lower at higher redshifts. So there's still an opportunity for AGN to switch on in these lower mass objects. So another thing we're looking at the moment is so we can see that a number of these objects in terms of their accretion rates, looking at their bolometric AGN luminosities, are very bright objects at redshift 6 or redshift 7. So the question is, are these very bright objects detected as AGN at these redshifts? Do they evolve into passive galaxies, and what's the fraction of them that do? So that's something that we're looking at in detail now. So I will finish up there. So just summarize some of the passive galaxy populations in flares. These will be accessible to JWST, obviously, as well in larger numbers, probably with Euclid and Roman. We're making predictions for that. Passive galaxies at Z equals 5 tend to form at least 50% of their stellar mass between redshift 6 and 8. And then the kind of passivity is driven by very early AGN feedback. So as mentioned, it's a kind of work in progress. I'm hoping to share something on the archive soon, but I'd be interested to hear anybody's comments or questions. Thank you very much for listening.
All right. Yeah, thanks, Chris. Really interesting stuff. So yeah, we have a couple of minutes for questions. I guess there's already one on the slide.
Yep. So the question is, do you also study the mass assembly history of these passive galaxies down to low redshift, for example, to determine the existence of a halo galaxy assembly bias?
Yeah, so that's a great question. So one of the drawbacks of our approach with flares is that we only run these regions down to redshift 4.7. So unfortunately, we can't follow these objects forward in time. We have talked about picking a few regions and running these lower to see what their kind of descendants look like. This gets complicated by how we weight the different regions. If you're interested in the statistics of the descendants, for example, but yeah, it's something that we've spoken about, but yeah, it's not trivial to do with the flare simulations. Whereas something like Eagle with the periodic ones, you obviously can do that, but then you're limited by not being able to predict that many passive objects at redshifts 5 and above.
You might have answered part of the question, but can you associate early time passive population with a certain low redshift population?
Okay, so one thing I didn't mention, I guess, is what's called the cluster eagle simulations. So these are what the name says on the tin, really. They are simulations of clusters at redshift 0. And they do have some high redshift snapshots. So these are obviously going to, for the most massive ones, going to trace these kind of protocluster environments that match some of the object or some of the regions we see in flares. So one thing we could do is look at some of the passive objects in those high redshift snapshots. Now, obviously, they will most likely end up as clusters in their descendants. So I'm not sure. Yeah. You're limited to make any kind of statistical inferences with that because it's not a statistically sampled population. They're just selected a range of clusters at redshift 0, different masses. So yeah, difficult, I'm afraid.
maybe one more question.
Sure, let's ask some more. Have you looked into what differentiates galaxies that are quenched by early AGN feedback from those that are not quenched?
Yes, so one of the things, again, I mentioned at the end is looking at this kind of AGN volumetric luminosity function and seeing, you know, which of these galaxies are quenched or not. But yeah, we've also looked at things like gas masses, the cold gas masses in these objects, whether they've had mergers, etc. I unfortunately don't have a nice statistical conclusion for you, but we've looked at a few different avenues for sure. And yeah, because of the way that FLARES is built, we can kind of compare that to the overall population, at least at that redshift.
Cool. There are more questions in the Slack, so maybe you can just continue the conversations on those there. Great talk again, thanks. And let's move on to Joachim Rosedal, who's going to tell us about Sphinx.
Thank you, Ramil. Can you hear me?
Yep.
Excellent. Good morning, good afternoon, and good night. I'm Joachim. Thanks to the organizers for having me here. So I'm going to focus this talk on the escape fraction of ionizing radiation from simulated galaxies and real galaxies as well. So observationally, we only really know about the escape fraction at low redshift. We know it's very low at low redshift. We don't know very much observationally at redshift beyond about 3. Theoretically, we need the escape fraction to be high at high redshift because otherwise we can't reionize the universe. So theoretical models have come up with forms of the escape fraction as a function of time that look you know, like this. They generally tend to increase with increasing redshift to conform to these observations and reionization. So it's hard to confirm this form of the escape fraction, and it's hard to explain. So my question is today, can we use simulations to verify this form of the escape fraction and to then try to understand why this happens? So for this, we use the Sphinx cosmological simulations. These are fully cosmological radiation hydrodynamical simulations containing about 25,000 star-forming galaxies at redshift 6. And the resolution is high enough that we can start to predict both the escape of ionizing radiation from individual galaxies without making assumptions, and the reionization history in the same simulation. So this mosaic is just supposed to give you a feeling for the kind of range of morphologies of galaxies that we have in those simulations. Just very quickly about the setup, we use the Ramses RT code, adaptive mesh refinement. We have volumes that are 10 and 20 co-moving megaparsec in width, physical resolution down to 10 parsec in the ISM of galaxies. We use a very bursty star formation, such that star formation efficiency locally can be very high, and that also leads to a very bursty feedback by supernova explosions. We include ionizing radiative transfer with the M1 method using the BPAS SCD model that gives us luminosities as a function of stellar radius and metallicities, and there is no calibration on unresolved escape fractions. So I just want to emphasize, this has actually been emphasized in a few talks already, that reionization is bursty and kind of flashy in those simulations. So here's an example of a galaxy, just one typical galaxy in Sphinx. You see the escape fractions in thick and ionizing luminosity in thin, which basically represents the star formation rate, which is very fluctuating. And the escape fraction kind of follows the fluctuations in star formation because the escape fraction is really regulated by feedback in those simulations. So I was tempted to show movies, but it's a bit dangerous on Zoom. So you can actually go to the Slack channel for this talk to see a couple of movies to see actually how the radiation is being flashed into the intergalactic medium in those simulations. Okay, so let's compare a bit to observations of the UV luminosity function at redshift 6. So the muted colors here show you observational data. The dashed curve is Sphinx intrinsic UV luminosities from the Sphinx galaxies. And if we take into account dust attenuation, we get a pretty good agreement with observations at all magnitudes that are included in the simulation. So this gives us a kind of good confidence that our galaxies are fairly realistic in their star formation rates. And the budget, more importantly, for reionization is more or less correct. We have the correct number of photons produced per volume in the simulation. Okay, so here is the reionization history in 3 variations of the Sphinx simulation. We're going to focus on this one, which is the largest volume that we have. It reionizes a bit late, even pushing the lateness that has been presented to us in previous talks in this conference. It's not too bad though. To show you the effect of volume size, you can see the yellow dotted curve. And you can also see the blue dotted curve, which shows you what happens if we switch just versions of the BPAS model. So you can see that, subtle modifications in the SSP model, they actually have huge impact on the reionization in these simulations via the escape fractions. Okay, so here are the escape fractions then, just global average, luminosity weighted average escape fractions in 2 versions of the Sphinx simulation, so smaller volume and larger volume, both with the newest version of BPAS. And indeed, pretty much like expected from these theoretical models, the escape fraction starts out high and then it does decrease with redshift. Not as much as in these models, but definitely this is something which is happening in the simulation. So that's very exciting. It's a kind of a verification, and now we can hopefully use the simulations to try to understand what is driving this evolution and the decreasing escape fractions with time. So going to the literature, there have been a few theories over the years of why such a thing could happen. First, there is an evolution towards more massive galaxies with time, and if we assume that more massive galaxies have lower escape fractions, as Anne was mentioning before, this would lead to a global decrease in the escape fraction. In just the same way, there is an evolution towards more metal-rich galaxies, and if they have lower escape fractions, this will also lead to the same thing. There have also been suggestions that there is a lower kind of intensity of star formation in the universe with time. And if we assume again that escape fractions are driven by feedback from star formation, then this should also lead to a decrease in escape fractions with time. So let's investigate this in the Sphinx simulations. First of all, here is the sensitivity or variance with escape fractions to the stellar mass of galaxies. So these are just bins of galaxies. Note that there's a huge scatter, but what you see here in blue is the mean escape fraction of galaxies given luminosity weighted mean escape fraction given a stellar mass. And you find that there is a distinct peak in the escape fraction at intermediate stellar masses of 10 to the 7 solar masses ish. And if you go to higher galaxy masses, there is a drop in escape fractions to almost 0 escape fraction at 10 to the 10 solar masses. So indeed, we predict, as many others have before, the escape fraction decreases with galaxy mass. You can see here in the red curve the cumulative intrinsic luminosity of galaxies below a given stellar mass. And then you can see in the purple curve just a convolution of the red and the blue. So basically an escaping luminosity below a given stellar mass. And you can see that the peak here and the drop in escape fraction, it shifts the escaping luminosity compared to the intrinsic one. Now for metallicity, there is a pretty much similar evolution. So at low metallicities, there is a relatively high escape fraction. And then with high metallicities approaching solar metallicity, it goes down to almost 0. So both factors in a sense could regulate an escape fraction that decreases with redshift. Given that there is an evolution towards higher metallicities and higher stellar mass. So now we look at the evolution of the escape fraction versus stellar mass versus galaxy mass with redshift. So this is just the same plot as I showed before. Before it was stacked overall redshifts, and now this is individual like redshift ranges. So now you see that the shape is pretty much always the same. There's always a peak around 10 to the 7 solar masses, but the magnitude is decreasing quite a bit with time. So for a given galaxy mass, the escape fraction decreases with time. So you can't then say that it's just the evolution towards more massive galaxies, which is regulating the escape fraction in this case. I'm not going to show it, but there's a very similar trend for metallicities. These also have the same shape, but decreasing magnitudes with time. So we can conclude from that neither the evolution towards more massive galaxies nor high metallicities is dominating the regulation in escape fractions decreasing with time. So now we can look at the intensity of star formation. We look at that in the form of the specific star formation rate. I'm going to say SSFR because it's a tongue twister. The specific star formation rate is just a star formation rate over the mass of the galaxy. And we look at the star formation rate over 10 million years, which means that the SSFR can be in the range 0 to 100 per gigayear. So now if you look at the evolution here of the specific star formation rate with redshift, we find that it does decrease with time. Okay, so good start. Then we plot the escape fraction versus the specific star formation rate of galaxies, again, across a range of redshifts. And first of all, there is a very distinct trend that galaxies with high specific star formation rates, they have the highest escape fractions. And if you go to lower SSFRs, lower escape fractions. If you look at now the shape and the magnitude of this relation, it pretty much stays constant over all redshifts, which does really indicate now that what's regulating the decrease in escape fractions is just the shift of this red curve here from being dominant at high specific star formation rates at high redshifts to being dominated by galaxies with low specific or relatively low specific star formation rates at low redshift. So to drive that a bit further home, we can try to isolate galaxies with specific star formation rates and see if they retain a constant escape fraction. If they do, then that's a very clear indication that the evolution in escape fraction is just dominated by galaxies shifting towards lower and lower specific star formation rates. Okay, so here is the global escape fraction for all the galaxies in the Sphinx volume. So now we take the galaxies with the highest specific star formation rates. These are enormous specific star formation rates. And if we only take those galaxies, they indeed do have a pretty much constant escape fraction over time. If you look at the shaded region, you find that the relative amount of ionizing luminosity being emitted by these galaxies is decreasing with time. And if you take the next spin in specific star formation rates, you again find a roughly constant escape fraction. And you see here how the luminosity is dominated by these galaxies. And we can continue. And then it becomes kind of obvious that the escape fraction is kind of constant for all classes of galaxies. But there is just a shift from the luminosity being dominated by high specific star formation rates to low specific star formation rates at low redshifts. So the evolution in escape fraction is there. And it is regulated by this decreasingly intense star formation in the universe. So that's all I wanted to say. I will just leave you with a summary here. I've done exactly 10 minutes, so I'm done. Thank you.
All right, thank you very much. That was really interesting stuff, amazing simulations. So yeah, we have some questions already on the chat.
So one question is, in the bursty star formation example, why is there a delay between UV luminosity and F escape for the second group of star formation events, but not for the first group, whether it's local density?
Whoa, that was a loaded question. Can you repeat that?
In the bursty star formation example, why is there a delay between UV luminosity and F escape for the second group of star formation events, but not for the first group?
I guess this is a reference to the plot here.
Yeah.
For an individual galaxy, it's a bit, things are very chaotic here, and nothing is kind of perfect. There is never a perfect trend between, sometimes you can have an intense episode of star formation, which is not followed by a high escape fraction. And even, possibly vice versa, things are kind of merging and there are accretion events. There's all kinds of stuff that complicates things. So I guess that's my answer, if I understood the question correctly.
Okay, if you're not, you can just answer that on Slack.
Absolutely. Yeah.
Another question is, in your model, to which UV luminosity do M star of 10 to the 7 galaxies roughly correspond?
10 to the 10,
10 to the 7.
10 to the 7,
10 to the 7.
So the peak.
Yep.
I think it's around -17, but I have to come back to that. So I have looked at it. I don't have the plot in this bunch of slides, but I think it's around -17.
And over what time scale is specific star formation rate averaged? Do you explore time delays, i.e., does F-escaping galaxies lack specific star formation rate bursts?
Yeah, so actually, there's a subtle point that I didn't really have time to discuss here. We look at specific star formation rates over 10 million years, indeed. As you can see here, we are also looking at maximum specific star formation rates over the last 100 million years. So if you only take galaxies that currently have high specific star formation rates, you don't get the same very nice trend. And that's because galaxies that have recently had high specific star formation rates, they tend to, if they have been very high, they tend to kind of blow up. And they go to very low specific star formation rates, but high escape fractions. And they can remain luminous for a few million years, maybe 20 million years, something like that. So therefore, it's important to look at recent high specific star formation rates rather than current ones.
We probably need to move on. There are more questions on the Slack. So Yoki, maybe just interact with people there. So we should probably move on to the last section, talk of the section. So thanks again, Yoki, that was excellent. So now we're on to Viola Gelli. So if you could share your screen.
So can you see it?
Yeah, we are good.
Okay, so I can start. So hello everyone, I am Viola Gelli, a second-year PhD student at the University of Florence. And today I'm going to tell you about dwarf satellites of high redshift Lyman break galaxies, a free lunch for JWST. So let me spend first few words on about why we are interested in dwarf galaxies at high redshift. And that is because they are the first galaxies that form in the universe. And they also represent the building blocks for the formation of more massive systems that we see today. And we know that JWST will provide for the first time direct observation of these faint objects, observing them directly during the epoch of ionization. But what do we know at present about these systems? Basically, our knowledge of dwarf galaxies comes mainly from detailed observations in the local group. And we know that here they live mainly as satellites of more massive systems like our Milky Way and Andromeda. And at high redshift, actually, we expect a similar situation. So we expect to find dwarf galaxies not only isolated in the field, but also living as satellites of typical massive systems there. So those are those massive galaxies that are typically observed as Lyman break galaxies. So this is a good news, let's say, because we know that already within the first surveys that JWST will perform, many Lyman break galaxies will be observed. So we asked ourselves, will JWST be able to detect for the first time the satellites of the massive Lyman break galaxies? To answer this question, I used an high-resolution cosmological simulation developed by Pallottini in 2017. And this simulation reproduces the properties of a typical Lyman break galaxy up to redshift 6. And here I show you a stellar density map of the galaxy, which is called Althea. And here in the center, you can see the face-on disk. And what I found is that inside the virial halo of Althea live 6 satellites. Their masses cover a wide range from 10 to the 6 to 10 to the 9 solar masses. And actually 5 of them are dwarf galaxies in the sense that they have their own subhalo of dark matter. But one of them, the smallest, S1, do not have dark matter, so we labeled it as something more similar to a protoglobular cluster. So in this first paper that was published last year, I studied in details the physical properties of these satellites. So these dwarf galaxies that live in these peculiar dense environments around Lyman break galaxies. And I'll now go through the main results. So I wanted to understand which mechanism drive the evolution of these systems, so I derived their star formation and metal enrichment histories. And I found that their behavior can be divided mainly into two categories according to their mass. Indeed, on one hand, we have the behavior of low-mass satellites. Here I show you the age metallicity relations along with the star formation history and the metallicity distribution function. So we see that these bone systems form all of their stars in two short and intense bursts of star formation, during which the metallicity increases in time. Also, we may notice that there is a first interruption of star formation and then a subsequent quenching, and both these features are due to the effect of the internal supernova feedback. So it is indeed the internal supernova feedback which is responsible and capable of completely suppressing the star formation in these small systems. On the other hand, we have high mass satellites, which can form stars for much longer times, and their metal enrichment history is more complicated, characterized by all these vertical trends, and each of them represent a merger event happening. So we have that merger events that are very common in these highly dense environments, are the mechanism that counteract the effect of internal supernova feedback and can allow star formation to go on for longer times in these massive systems. We also may notice that both type of satellites are very rapidly enriched up to solar values. So these systems are typically more metal rich than typical dwarf galaxies that live isolated in the field. But if we check the amount of metal poor stars composing their stellar populations, so these, we have that lower massive systems have a higher amount of metal poor stars. Indeed, if here I plot the fraction of metal poor stars as a function of the halo mass for the 6 satellites and for the central LBG, and these clearly show a decreasing trend, meaning that lower massive systems are dominated by metal poor stars. So now that we've seen the main evolutionary and chemical properties of these dwarf satellites, we can move on to answering our main question. So will the stellar emission of these objects be observable with GWST? So with this aim in mind, I modeled the stellar emission and dust absorption of each system. And here I show you the spectra of the satellite along with the one of the central LBG Althea. And I chose to show you these spectra for 2 relevant stages during their evolution. Indeed, at redshift 6.5, we have that the low mass systems are experiencing their short burst of star formation. So in this stage, their spectra, as we can see here, are peaked at a lower wavelength. Here, instead, at redshift 6, they had already been completely quenched, as we saw before, by supernova feedback. So their spectra are passive, so are fainter and dominated in general by older stellar populations. Also, we may notice these horizontal lines that represent typical sensitivities for the NIRCam instrument on GWST, and this gives us an idea of what we'll be able to detect. For instance, if you remember the small protoglobular cluster which I showed you before, we have that its emission is not shown here because it's well below these limits, so it will most likely not be detectable. But all the other satellites have fluxes comparable or above these limits, meaning that they will be detectable. However, to understand if their emission will effectively be resolved from the one of the central LBG, I needed to consider also the spatial resolution of the instrument. So here I show you these synthetic images of the system at redshift 6, as will be observed with the near-infrared camera of GWST. I show you the result for 2 filters and 2 different exposure times. where 20 hours is the typical time that will be reached by the deepest starbase with JWST. And these images show that the emission of all the 5 satellites will be observed in 20 hours of observation, but also that in just 3 hours, it will be possible to catch the light from the 2 most massive systems. Also, we see that if a system is located below about 0.2 arcseconds, so like in our case, the satellite S5, it will be difficult to disentangle its emission from the one of the central galaxy Althea. But all the other galaxies are actually well resolved, so we will be able to easily identify these systems as dwarf satellite galaxies. At this point, we also took a step farther, and we wanted to try to understand if already just with imaging and photometry, it will be possible to derive some properties of the satellites. So I produced these color magnitude diagrams that show us how the colors and magnitude of the systems change during their evolution. And these are color coded according to different physical quantities. So what we learned from here is that, for instance, we found that satellites with this color below minus 0.25 will identify star-busting low-mass dwarf galaxies, which are dominated by young and metal-poor stars. So here I leave with you my conclusions. Basically, the takeaway point is that we study these new class of high redshift dwarf galaxies, which are different from those living isolated in the field, because these ones live in dense environments as satellites of massive Lyman break galaxies. And we demonstrated that they will be observed already within the first starbase with the NIRCam instrument, and also they will be easily identified in the surrounding of Lyman break galaxies, hence providing a free lunch for JWST. Thank you. I'm happy to take questions.
Thanks. That's yeah, very interesting simulations. Yeah, so if you have any questions, you can post them in the Slack. So just a quick question of clarification, I guess. The star formation model does account for a metallicity dependence, or in some way, or H2? Yes.
Yes, sure. When I model the spectra, I take into account the age of the stellar population, the metallicity, and also.
Well, I was asking more about the. I was asking more about the actual star formation recipe in the simulation itself.
Yes, it takes into account the metallicity. Yes. But also, yes, I meant also for the modeling of their CD, of course, I took into account all of that.
Yes, great.
Mm-hmm.
So there's a question in Slack asking, how lensing
Sorry,
can
I
help
can't
boost up
hear
the
you
detectability. Sorry,
I didn't hear you.
It will be good to estimate how lensing can boost up the detectability.
Yeah, sure. That will be really interesting because it will definitely boost. But actually, we know that, for instance, within the JADE surveys, there will be I think no lenses. But already without lensing, we can do, so much. So even without lensing, here we see that many dwarf galaxies will be resolved in also more than 1 pixel. And so they will be easily identified. And also one thing that I did not say is that these images that I show here are for redshift 6, which, if you remember, is the phase when these galaxies are passive. So this is the faintest stage, let's say, during the evolution of these galaxies. So already at the faintest stage, we will be able to identify them. So even at, let's say, as previous stage with respect to redshift 6, the emission will be even more. So it will be possible even without the lensing.
Next question is, do you have any ideas to distinguish the satellites and star-forming clumps with a galaxy with JWST?
Do you mean to distinguish, yes, satellites from star-forming clumps? Yep. Okay. Well, actually, that was the point of, let's say, the fact that the prosoglobular cluster, the one that we called prosoglobular cluster, is actually just a clump of also gravitating stars. But the difference, the main difference, I mean, physical of that object and our satellites is that within the simulation, it has no dark matter at all. While our satellites do have their subhalo of dark matter. And actually, our results tell us that the galaxies, these galaxies that have their halo of dark matter will be observable, whilst typically prosoglobular cluster and I think also small clumps within the halo won't be observable because their flux will be much lower, let's say, with respect to these limits. And also, of course, there's this problem of, I mean, clumps living within the disk will be difficult to disentangle their emission just for a resolution problem. So I think those independent objects located in about 0.2 arc seconds will be definitely dwarf satellites, galaxies.
Yeah, okay. So there are more questions in the Slack, but I think our time is up. So maybe Viola, make sure and take a look at the Slack.
Sure.
Yeah, well, thanks very much to all the speakers. It was a really interesting session. And I guess we're restarting in about an hour and 45 minutes. So that's 13:30 UTC. So we will see you all there. All right.